Hello everyone, welcome to this 7th lecture in the NPTEL course on Riemannian geometry. So today we are now done with sort of quick review of smooth manifolds. So today we'll really begin our study of Riemannian manifolds. So the central notion in the field is of course that of a Riemannian metric. Okay, so let me go straight to the definition. So a Riemannian metric on M. So from now on I am not going to keep repeating this, but M is going to be an n-dimensional smooth manifold unless otherwise stated, right. So so Riemannian metric on M is a 0 to tensor which is usually denoted by G. So this is a 0 to tensor which additionally is symmetric So that means for all vector fields x y, g of x comma y, this is a smooth function by the definition of tensors. This is the same as g of y comma x. Okay, and the second property we need is positive definiteness. Which means that for all so G has to be positive definite, okay, which means that for all vector fields x and all points P in M, if you calculate this, this is bigger than or equal to 0. So G applied to x comma x is bigger than or equal to 0 with equality if and only if this vector xp is 0. Right. So note here we are using the property that if you have a tensor, then that will actually induce a multilinear product on the cotangent spaces and the tangent spaces at that point, right. So that is what we mean when we write GP. So that's the induced, so here GP is the induced bilinear product on the tangent space, okay. So any 0 to tensor which is symmetric and positive definite is called a Riemannian metric, okay. And then a Riemannian manifold is a pair Mg where G is a Riemannian metric on the manifold M, okay. All right, so given a Riemannian metric, we have the following geometric notions. We can define the following geometric quantities. So firstly we can define a norm or a norm function. Okay, so what is the norm function? The norm function will basically take in a vector field and spit out a positive smooth function or a non-negative smooth function. So it sends a vector field x to basically the square root of the tensor evaluated on x comma x. Okay, so similarly one can localize this to a single point. So at a single point this gives you a norm on the tangent space at that point. Okay, so the vector xp goes to gp of xp comma xp and the square root of that. Yeah. Secondly, given a Riemannian metric, I can define lengths of curves. So suppose gamma is a smooth curve, then the length of gamma is defined to be the integral from a to b of, you compute the velocity vector of gamma, compute the norm of that and integrate that from a to b. Okay, so here recall that the velocity vector of gamma, so this ought to be a vector field along gamma, so it acts on a germ at a point gamma of t, and this is basically just the usual derivative of f composed with gamma, right. So that's defined to be the velocity vector of gamma, and then you just compute the norm using this norm function and integrate that on this interval a to b. So that gives you a way to calculate. Suppose you have a manifold and you have a curve, you can now compute the length of this curve. And finally, a Riemannian metric also helps you compute angles between tangent vectors. So you define the angle between the tangent vector by this relation. So given, let's say, u and v in the tangent space at a point P, you define the angle between u and v to be simply the arc cosine of the inner product of these two divided by the norms, the product of the norms of these two. Okay. So that's defined to be the angle, and by definition arc cos takes values between 0 and pi. Okay. All right. So let me also introduce some notation, because it's sometimes cumbersome to keep writing g all the time. So sometimes I'll also write g of xy to simply be this angular brackets x comma y. Okay, so I'll use both notations interchangeably. All right, so locally, so suppose x1 up to xn are let's say coordinates on some open set U, then we already saw that a tensor, a 0-2 tensor can be written in this form. Okay, where Gij is a smooth function on this open set for each of these indices I and j, right? So the collection of all these Gij's, I can think of it as a matrix. So we set capital G of x to simply be the collection of these Gij's of x, where I and j vary from 1 all the way up to n. Okay. So then for each x in U, G of x is a symmetric and positive definite matrix. So also in terms of my basis for the tangent space, what are these components? Well, Gij is basically just the inner product of del I with del j. Okay, recall that del I was just this partial derivative in the ith direction. Okay, so these components Gij are precisely del I comma del j. Okay, so now if x and y are two vector fields, right, such that locally I can write x as summation I going from 1 to n xi del I, and I can write y summation say j going from 1 to n of yj del j. Okay, then the inner product of these two is simply given by summation ij going from 1 to n xi yj times gij. Okay, so given two vector fields, this is what I mean, this formula basically computes the inner product g applied to x comma y. Okay, so there is a convenient shorthand we can use. So if you take for this vector field, if you take the following vector, you think of these components x1 up to xn as column vectors, as a column vector. Similarly, you take these components, put them in the form of a column vector. So this is of course all happening on this coordinate chart U, where xi's are smooth functions on U, yj's are smooth functions on U. Then this is precisely, I mean, restricted to U. This is precisely the transpose of this vector times this matrix capital G, whose components are given by Gij, times the vector y. Okay. So this is a useful shorthand for the inner product of two vector fields on this coordinate neighborhood. All right. So now this G note was with respect to the coordinates given by x1 up to xn. So now what happens if you change your coordinates, right? How does this matrix change? So suppose x1 tilde x2 tilde up to xn tilde is another set of coordinates on some neighborhood u tilde, right. So then on the intersection we have this matrix G with respect to the original coordinate system x1 to xn. So this is with respect to the coordinate system x1 to xn, and G tilde with respect to the coordinate system x1 tilde up to xn tilde. So the question is, how do you go back and forth between these two matrices? What is the relationship between these two matrices? Okay, so recall that so with respect to this new basis, I can write down for the same vector fields that I had, I can write down x as summation xi tilde del I tilde and y as summation yj tilde del j tilde, right, with respect to the basis for the tangent space coming from these coordinates. So I then consider the corresponding column vector which is given by these components. Okay. So then what is the inner product of x y? If I use this coordinate system, then this is precisely the transpose of this vector times G tilde times this vector, right. But what is this vector in terms of the original vector? It's easy to check that this is precisely this. You have these transformation formulas. So if you plug these in, you get that x comma y is x transpose del x by del x tilde transpose times G tilde times del x by del x tilde times y. But remember, this was also x transpose times G times y. So now if you set these two equal to each other, you get a formula relating G to G tilde. Okay, so let me write that out in the next page. So we get the following transformation formula, that G is del x by del x tilde transpose times G tilde times del x by del x tilde. Okay. All right. So let's now maybe look at a few examples. So the first basic example is the flat or the standard Euclidean metric, which I will denote by GRN on the Euclidean space Rn. So Rn of course has global coordinates, So in components, this is precisely just dxi tensored with dxi. Okay, or sometimes one also writes this as dxi squared. Okay. So the corresponding capital G matrix here is precisely just the identity matrix, right? And how do you calculate inner products of tangent vectors? So if u and v are tangent vectors at any point in Rn, then you compute u and v. This is simply ui times vi. So essentially this is the standard dot product from linear algebra or from vector algebra, right? So this particular metric, this defines a Riemannian metric on Rn. It's called the standard or the flat Euclidean metric. So sometimes it's advantageous to look at a particular metric from in different coordinates, because again, for the given problem at hand, I mean this is written in terms of Cartesian coordinates, right? These are the Cartesian coordinates. So sometimes it's useful to think of other coordinate systems. So let me maybe talk about the spherical coordinates. So I want to now write the Euclidean metric in R3 in spherical coordinates. So one way to do this is to just use this change of coordinate formula, right? But on the other hand, you'll see that in actual problems it's much easier to just sit down and calculate from the beginning. So that is what I'll do here. I just want to demonstrate how this is done in a simple example. So recall the spherical coordinates. So what are the spherical coordinates? So the picture is you have a point here. You take the radial line. Sorry. So you take the radial line connecting these two. The distance of this point from the origin, that is called phi. The angle that you make, that this radial line makes with the z axis, is called the azimuthal angle phi. So this phi is going to be some angle in 0 and pi, and then you project this down to the xy plane, and the resulting line connecting this to the origin in the xy plane makes an angle theta with the x axis. So this is the x axis. So these rho, theta, phi are called spherical coordinates. Okay, and they work on all of R3 minus the place where rho is 0 and the place where theta is pi. So theta angle is always chosen to be between minus pi to pi. Okay. All right. So yeah, and phi is 0 or pi. So these two are ignored, right? So in terms of the spherical coordinates, how do the spherical coordinates relate to the Cartesian coordinates? Well, x is given by rho cos theta sin phi, y is given by rho sin theta sin phi, and z is given by rho cos phi. Okay, so now one can calculate what del by, for instance, del rho is. So that is del x by del rho times del by del x plus del y by del rho times del by del y plus del z by del rho del by del z. So what is this? What is del x by del rho? That's just cos theta sin phi del x plus what is del y by del rho? That is just sin theta sin phi del y plus cos phi del z. Similarly, one can calculate what is del theta. So you differentiate each of the components with respect to theta. So you get minus rho sin theta sin phi in the del x direction plus rho cos theta sin phi in the y direction plus 0 in the z direction, because this does not have any theta, right? Similarly, you can write down what d phi is. So that is rho cos theta cos phi del x plus rho sin theta cos phi del y minus rho sin phi del z. So now you just calculate what to write down the metric in terms of these spherical coordinates. You basically need to calculate these things. So sorry, your matrix G for the spherical coordinates will basically be something like this: del rho, del rho, del rho, del theta, del rho, del phi, and so on. So you can calculate all of this carefully using the fact that the G for the Euclidean metric in the Cartesian coordinates was basically the identity matrix. Okay, so that basically means that del x is equal to del x del y is equal to del z is equal to 1, and the rest of the inner products are 0. So using that, if you do this calculation, I'm not going to write out all the calculations. You can actually check that that this is given by d rho squared plus rho squared d phi squared plus rho squared sin squared phi d theta squared. So the same flat Euclidean metric in spherical coordinates has this formula. Okay. Alright, maybe I'll do another example and then state sort of a general fact. So one can also write down a product metric. So suppose you have two Riemannian manifolds Mg and n comma h. Then on the product M cross n, which is a smooth manifold again, one can define the product Riemannian metric in the following way. So if recall that the tangent space of the product at any point p comma q, the tangent space of the product splits as the tangent space of M plus direct sum the tangent space of N, right? So given any vector uv in the tangent space here, any vector let's say given any vector u1 v1 in this tangent space and u2 v2, then one can define the inner product of u1 v1 comma u2 v2 in this product metric now to be simply the inner product of u1 u2 plus the inner product of v1 v2. Okay, and it's an easy matter to check that this actually defines a Riemannian metric. So this metric is called the product metric. Okay, let me end this lecture with the following important proposition. So of course we have defined this notion of Riemannian metrics. You might wonder whether do these objects actually exist, right? Does there actually exist a Riemannian metric on a smooth manifold? So in fact there does. So on any smooth manifold, there exists a Riemannian metric. Okay, and in fact there exists uncountably many. So let me quickly give you a proof of this. So let U alpha be a cover of M by coordinate neighborhoods with coordinates x alpha 1 up to x alpha n. So this subscript of alpha denotes that I am working on this coordinate neighborhood U alpha. Okay. So the picture is as follows. So we have, so this is this U alpha, you might have another U beta and so on, right. So the idea is that on this U alpha, sorry, so there is this U alpha. On this U alpha, you have this map phi alpha to Rn, right? And similarly on this, you have a map phi beta to Rn. So the idea is on Rn, I have a Riemannian metric, the standard flat Euclidean metric. So using this map, I am going to transport this metric back onto this open set U alpha. Similarly on U beta, I am going to transfer the inner product to some inner product on U beta, and then in order to get a global Riemannian metric, I am going to glue these together using a partition of unity. Okay, so let me write down the details. So on U alpha, we have the Riemannian metric G alpha, which is given by summation I going from 1 to n of dx alpha I tensored with dx alpha I, right. So this is the standard Euclidean metric on this coordinate neighborhood U alpha. Now to consider a global thing, we consider the following Riemannian metric. You just take the sum of all these Riemannian metrics multiplied by rho alpha, where rho alpha is a partition of unity subordinate to this cover U alpha. Okay, so this formula one can check defines a global symmetric 0 2 tensor which is positive definite, and hence it defines a Riemannian metric on M. Okay, so I'll leave the details as an exercise. You have to check that this defines a symmetric tensor and that this defines a positive definite tensor, and all of this follows because G alphas define a symmetric and positive definite tensor, and recall that rho alphas are always non-negative, and at any given point summation rho alpha at any given point is 1. Okay, so so you're never going to get that this is actually 0, so you're also going to be able to prove positive definiteness, okay, just from the properties of partitions of unity. So I'll leave this as a nice exercise for you to check. Okay, so so maybe let me end with the following comment. So let me end with the following sort of comment on rescaling. So given a metric G on M, if lambda is some positive number, then you can define another I mean you can define G tilde to be lambda times G. So this is another Riemannian metric. Okay, so the properties of this is that it distorts lengths but preserves angles. So if you go back to the definition of angles, you can check that this actually preserves angles, but of course if lambda is bigger than 1, then it will sort of expand the distances. If lambda is less than 1, it will shrink the distances, but it preserves angles. So G tilde is called a rescaling of G. So one can actually take this a bit further. More generally, you take a function lambda from M to the positive real numbers. So lambda is a smooth function. Then G tilde, again defined to be lambda times G, is a Riemannian metric. Okay, so in this case, if you are multiplying by a function instead of just a number, this is called a conformal rescaling. Okay, so this again distorts lengths but preserves angles. Okay, all right. So maybe I'll stop here for now. In the next lecture, we'll look at more examples of Riemannian manifolds. Okay, more examples of Riemannian metrics. All right. So that's it for this lecture. Thanks for the attention, and I'll see you in the next lecture.